Okay. Right, so you can see the questions now. Right. So let's say we have a question like this. All right, so we are attaching a rock at the end of a meter stick. All right, and you see that we want to balance that. All right, we want to balance the meter stick.
Oh, excuse me, doctor. Are you sharing the question now?
I share the screen, right?
I think you have to share again because
Oh, you cannot see the.
yes.
All right, let me share it again.
See you there.
Okay, you can see the question now.
Yes.
All right. Okay, so you have a rock attached at the end of a meter stick, and then you want to balance that meter stick. Okay, so we are going to determine how far, right, from the left end, okay, of the stick should the triangular object be placed, right? So how do you know that? Okay. Okay, so you have a meter stick, so meaning that, all right, so meaning that the meter stick is 1 meter, right? It's 1 meter. Okay, so basically you know the length of that stick. Okay, and then you have the mass given. Mass of the meter stick is similar to the mass of the rock, which is m. Okay, so what is the equation that you can use over here? What is the equation that you can use over here? So who can tell me what kind of equation that you can use? I have shared you the whiteboard, right? If you want to give me the equation, so you can put it there. All right, so we solved this last Thursday. Anyone? If you don't remember, you can open back the notes, okay, that I shared you last week on the chapter 11. Anyone? Okay, so you have no idea how to do that. Check back at the example 11.1. right? Check back example 11.1. So you will have an idea on how to do that. Okay, basically, the center, okay, the center will be at 0.5 meter, right? So the center will be at 0.5 meter. So the center will be somewhere over here, over there. Okay. So you need to know, okay, what is this? So that's, I assume that S and X. Okay. So how do you solve this? Okay, so you need to define, okay, you need to define first what is this, the length, okay, the center of the mass, okay, to the to the this mass, okay, and also another one, okay, due to the rod mass, okay, to here, to that. So I assume that S and A, okay, and this one due to this one, okay, that will be 0, right? Okay, so any of you can write something over here. So X is equals to M, so which is the mass of the stick times 0, because the length is 0, okay, because it's at the center of that, and then the mass times M, okay, which is 0.5. 0.5, and then you need to divide that. You need to divide that, okay, with M plus M. Okay, so what is the answer? Okay, who chose A? Who chose A? You can raise your hand. You can raise your hand. Nobody to say. So how about B? Nobody choose B. How about C? Nobody choose C. And how about D? You don't have any idea on how to solve this? I already gave you part of the solution. So I already wrote you the part of the solution on the whiteboard. You can see that it is, so when you solve that, so X will be equals to M times 0 plus M times 0.5. Divide with M plus M. So M plus M will be 2M. So M times 0.5 divide with 2M. So what's the answer? It should be this one, right? 0.5. Okay, it should be B. Do you get that? So x is m times 0 plus m times 0.5 divided with m plus m, which is 2m. So you solve this, so you obtain 0.25 meter. Right? Okay. All right. Let's discuss another one. Right. Okay. So we have a metal advertising sign. Okay. With weight of W is suspended from the end of a massless rod of length L. Okay. So this rod. Okay. This rod. Okay. The mass is 0. Okay. So we assume that the mass is 0, although it has certain mass. So maybe it's very, very small, so you can ignore that. Okay, the rod is supported at the end by a hinge at a point P. Okay, so there's a hinge over here. Okay, and at the end by a cable. Okay, so you have a cable over here. Cable over here and also a cable over there. All right. So which this cable make an angle with the rod, okay, as theta. What is the tension in the cable? All right, so how you solve that? Okay, how do you solve that? So how do you know what is the tension of the cable? Okay, what is the tension of the cable? Any idea? You can, any one of you can, yeah, can suggest me, and you can talk. It's not a problem. It doesn't mean, okay, your solution is correct or wrong. So we might learn together. Okay, so you have the theta over there, right? So you have the height, right? You have the height, okay, and you know that the signboard, all right. So that's the dinosaur. The dinosaur is a signboard, right? As you can see that. So it has certain weight of W, okay. So what is the tension, right? So what is the tension over there? Give me a while. Okay, so what's the tension over there? So you can refer back this one in the slide.
Okay, masuk yang lain.
Okay, you can check that, right? So you need to find out what is the force acting on that in terms of X and Y. So that's the first rule when you are trying to solve the problem. Okay, so you have A, T equals to W sine theta. So you already see that all of the solution is related to the sine theta and also cos theta. So you just need to choose whether it is related to cos theta or sine theta. Okay, so what is the tension over there? So the tension, all right, must be, okay, so somewhere, so it's W over there. So the tension is the force acting, okay, somehow, all right. So in this cable, okay, it is asking you on this table, what is the tension there? Okay, so it has a X component and also Y component. Okay. So your X, okay, your Tx and also Ty. So how do you solve that? So who got the answer as A? Who got the answer as A? Okay, Shazia2 choose A. And how about B? I mean, you also choose A or B? Okay, who choose B? How about C? Okay, area choose C. Okay, Jai. Okay, so Sim also choose C. Okay, how about D? Okay, nobody choose D. So, okay, majority of you. So, two of you choose A, and then three of you choose C. All right. So, maybe Amin can share how you calculate, you get A. Can you tell me, Amin, how you get?
I think W same with H, so we can use sine theta.
Okay,
That's it.
W
Yep.
is equal to H. All right.
So we can use W sine theta to find the tension.
Okay, so you mean that so sine theta equals to
T's.
T over W.
Yep.
Is this what you mean? All right.
T sine theta.
T sine theta.
T sine theta equals W.
This one. You mean T sine theta?
T sine theta equals to W.
Could you turn a little bit your volume up, Kalian?
Oh, sorry. Can you hear me now? Hello?
Yes, yes.
Oh, I mean T sine theta equals W.
Okay, T sine theta.
Yeah, T sine theta equals W.
Okay, equals W. All right. So which one is T sine theta? Okay, this component or that component? So which one is your t sine theta? This one, right? Tx.
Yes.
Okay, so your Tx is equals to W. So, okay, so you have this relationship, right? So, okay, so this is correct. Okay, so you have this, right? So how do you obtain it? Because why you choose this, all right? Because you need to find out what is your Tx. So your Tx will be equals to W, all right? So the force on the Y is cancelled out, right? Because over here, Ty will be, okay, will be 0, okay? Because over here, there is no other force acting to that direction, okay? And but Tx, okay, Tx is equals to W because the net force will cancel out the force going down and also the force going up. Okay, so that's why you have T sine theta equals to W. Okay, according to this, okay, which one is your answer? Again. Okay, anyone choose A? Anyone choose B? Anyone choose C? Okay, still the same person, right? And anyone choose D, you still don't get the answer. So the answer is C, right? Based on this equation, right? So T is, so you just rearrange this, W over sine theta. Okay, good. All right, thank you, Kaliang. Um, as a bonus, I'm going to give a bonus mark to Kaliang. All right.
Doctor, actually,
Yes.
I just help my friends to answer because the chat box there, they are responding there. Yeah, so so
Oh,
I'm
okay.
the same thinking, so I
All right.
just
Thank
answer you
you.
because no one opens mic. Yeah.
All right. All right. Thank you. I didn't check the
Yeah.
slide slope. Okay.
Yeah.
Never mind. All right. You're going to look after this. All right. Again. By the meantime. Okay. Okay. Thank you, Kaliang. All right. So. Okay. Good. Okay. So Alia got it correct for the first one. All right. Okay. Alif got is correct for the first one. Elia got it correct. Okay. Okay, Min, so you need to change that. Okay, so it's C. Yeah, you also got it correct. Okay. All right. Um, okay, let's me look for another example after this. All right. So let's go back to chapter 12. Okay, I'm going to take note who already answered that. Okay, so Alif, Elia, and also okay, Hai Liang. All right. So I'm going to give you some bonus mark, all right, to your mark, to your grade, all right. Give me a couple of seconds to take note on your name. Okay, so now let's go back to our lesson, right? So which is on the chapter 12. So we will continue doing the problem solving later after we get some break. Okay. Okay. All right. So we are now going to learn about the fluid mechanics. So before this, we learned so much about the rotational dynamics. All right. Now we learn about the fluid. And just before the chapter 11, we learn about the wave, right? Sorry, we learn about the equilibrium. Okay, so this is basically what you will be learning in this chapter. Okay, so about the density and pressure, okay, Bernoulli's equation, okay, and the viscosity and the turbulent flow. Okay, so look at the fish there. So we have a colorful tail spot rest is 10 centimeter long and can float in the ocean with a little effort. Okay, so you see a bigger fish, right? A manta ray, okay, is more than 5 meters across and must flap its fins continuously to keep from sinking. Okay, so the phenomena over here is related to the fluid mechanics. Okay, so first we need to look, so as a principle of physics, so we have the rest and motion condition. Okay, so first we're going to look in the rest at the rest condition. Okay, the fluid at the rest condition, and also next when the object is moving. Okay, inside the fluid. Okay, so you are familiar with this one. So I believe you are familiar with the equation of density. So density is equals to mass over volume. All right. So density is a very important property of any material, okay, of a fluid or solid. Okay. All right. So the density will be similar. All right, will be similar for a homogeneous material. All right. So mean that the homogeneous material is the one that have similar composition of material, okay, such as a okay, such as an ice. Okay, so ice is made of the water, but if the material is mixed, okay, so like you are making a chocolate ice, right? A chocolate ice, so that is not a homogeneous material because it's mixed with uh, a chocolate and water. So for homogeneous, so it is just a pure material. Okay. So for example, in the ice, so we only have the water. So that's why we call that as homogeneous. All right. So for that homogeneous material, we have the same density. Okay. Everywhere, if we measure. Okay. If we measure on the solid. Okay. On the volume. Okay, so we have, for example, here we have a steel wrench and a steel nail. Okay, so these are made of steel, right? So steel is a homogeneous material. Okay, so but what we want to know over here is they have the similar density. So why it has a similar density, even though the steel wrench is bigger than the steel nail? Okay, so it's because of due to this equation. Okay, so mass over volume. All right, so even though the mass of steel wrench, okay, is larger than this, okay, so this mass is lower, but the volume is also lower on the steel nail, but compared to the volume of that, which is bigger. So that's why we have the similar row, nail and wrench. Okay, so these are some common density, okay, for a couple of substances. So you can just look over the table. Okay. Okay, let's look into the meaning of pressure. Okay, pressure in the liquid. Okay, so the pressure at a point in a liquid is defined as P equals to dF, okay, over dA. So we have the shift. Okay, we have the shift in terms of force and also over certain area. All right. So that's a pressure at a point in a fluid. Okay. So pressure is F over A. Okay. So we have the force. Okay. If we have the force, okay, if the force is not net, okay, we did meaning that it is not zero, then of course we will have a certain pressure. Okay, and then we divide that with a area. Okay, so let's say I stretch my shirt over here, so we have a certain pressure on acting on the shirt, okay, because the material is stretched. Okay, so how do you calculate the pressure? So you need to define how much force that you give to the shirt. Okay, you need to divide that with the area of the shirt material that involved when you apply the force. Okay, so that is similar inside a liquid. Okay. Okay, so this is you can how you can imagine that, all right, inside the water, okay, inside a fluid. So fluid also have a certain pressure. Okay, fluid also have a certain pressure. Okay, pressure. Okay, so you look that. So we can measure at any orientation. Okay, at any orientation. Okay, so as long as the area that we cover, okay, we apply the force is similar, then the pressure will be similar. So you compare this one, right, with this one. Okay, so there are two different surface that you consider. So the one is horizontal and the other one is vertical. Okay, and then you apply the force to that, and then the other one you apply the force from the top to the bottom. Okay, it's still similar, right? It is still similar pressure. Okay, because you relate back to the previous equation, P equals to F over A. Even though this is F over A, and this one is 2F over 2A. Okay, so it is still a similar pressure. Okay, so let's say we have a certain depth. Okay, let's say inside the ocean, right? We want to measure the pressure. Okay, so you can measure pressure, okay, inside an ocean. Let's say a few meters below, okay, below the ocean. So how you can measure that? Okay, so you have a pressure at the top of the ocean, okay, at the surface of the ocean, okay, and then down there okay, you want to calculate the pressure over here. So the pressure over here will count, okay, the height. Okay, will account the height between the surface and also at the point where are you measuring the pressure. Okay, so how do you find this? Okay, you add the pressure over here and then with the height, okay, times the, as you have here, the gravitational acceleration, okay, and also rho. So rho is the density. Okay, so that's how you calculate the pressure at a certain point below the ocean. Okay, so let's look at an example here. Okay, this is the normal
manometer tube is partially filled with water.
physics
Oil is
concept
then poured into
where
a
I believe you
tube
have
until
learned
the oil-water
before.
interface is at the midpoint of the tube as shown in this diagram. The oil and the water don't mix, hence the system remains in static equilibrium, and I'd like to calculate the relationship between the height of the oil and the height of the water. I'm going to approach this problem using equation 12.6, which gives me the absolute pressure at a depth h in a fluid. And I'm going to calculate the pressure at the bottom of the tube from two perspectives. One looking this way at a depth h water, and the other looking to the right at a depth h oil. And I can immediately write down those two pressures as shown here, where P naught is atmospheric pressure at the top of both fluids. These two pressures have to give me the same value at the bottom of the tube for the system to remain in static equilibrium, so I set them equal to each other. Of course, these cancel, and the G's going to cancel. And I can now solve for the height of the oil as a function of the height of the water. The density of water is about 1,000, density of oil about 850, so oil is less dense than water, so the height of the oil has to be greater than the height of the water, as shown in the diagram. And this ends example 12.4.
Okay, so over here you can actually relate. Okay, you can actually relate the density. Okay, the density of the water and also the density of the oil, right? So it is easy because at the point P, right, the pressure will be similar, all right, for both water and oil. Okay, but the difference is, okay, what's the difference? So the difference is that you have a difference of density, okay, and also the height of water and also the height of the oil. Okay, so that's the difference. Okay, but your initial pressure, okay, your initial pressure will be similar, okay, for both the density and fluid, okay, sorry, for both water and the oil, okay. So you have P naught, okay, a density at the surface of a liquid will be similar, okay. So you have similar P and also similar P naught. Okay, so this one, okay, you rewrite that again. First in terms of the water, and another one is in terms of density of oil. So you can equate that equation. Okay, so once you equate the equation, so you can cross out P naught. Okay, and then what is left is rho water, okay, G and H. Okay, and then rho oil, G and H of oil. Okay, so G is also can be crossed out, okay, because the gravitational acceleration is similar for both of water and oil. So this is, so rho water times H water equals to rho oil, H oil. So that's the relationship. Okay, so you obtain whether if you want to take the H water, so H water equals to rho oil over raw water times H oil, or H oil equals to raw water over raw oil times H water. So either of that are correct. So either of that is correct. Okay. Okay, so that's the relationship. Okay. Right. So we have over here. Okay, each fluid column has the same height, no matter what is shape. Okay. So it doesn't matter either it's curvy, all right, either it's curvy or you have a U shape or whatever. So either is like that, okay, it is like that, okay, doesn't matter, you just count for the height, okay, the vertical height, okay, in order to calculate the pressure. Okay, so that's how all of this liquid, okay, all of this liquid, if you account for the P over there, P somewhere over there or somewhere over there, will be similar for all of those liquid. Okay. Okay, so the pressure is the unit is Pascal, all right? So unit is Pascal. So we have the Pascal law, all right? So what is the statement of the Pascal law? So we have pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and the walls of the containing vessel. Okay, so meaning that if we have this, right, example over here, okay, the pressure, the pressure acting, okay, on this, right? So you have a net force. Okay, you have a net force. Right. So what you can relate is P is F1 over P is equals to F1 over A1 and also equals to F2 over A2. Okay. So that's the relationship. Okay, what you can observe also over here, we have PA1. So PA1 is equals to F1. Okay, so basically F1 is equals to PA1. So when there is a force, okay, acting downwards, so you can account that the force acting upwards. Okay, so you have the net force acting on this structure. Okay, so as you look over here, these two pressure applied over here, okay, has, okay, similar height. Okay, it has similar height. Okay, so that's why the pressure, the force applied upwards over here, it is actually equals to the force applied over here as well, even though the force applied over here is much smaller than this one. Okay, but the difference is the beauty of the Pascal law is that the pressure is similar. Okay, similar when you have a similar height. Okay, so that's why it is important to note that the pressure, okay, the pressure is similar everywhere when you have the same height. Okay, so that's why when you are measuring, okay, when you are measuring the pressure, you only consider the height. So let's say you have a mountain over here. Okay, this is the ground, and then this is the ocean, for example. All right, so that's the ocean. So how do you quantify if you are there and you are also swimming there, okay, inside the ocean, for example? Okay, it's all counted based on the height. Okay. So the pressure that you feel on the top of the mountain, okay, will be, okay, will be 2 times lesser than what you feel, okay, what you feel when you are inside the ocean. So the pressure over here, okay, inside here will be much higher, 2 times compared to the pressure that you feel at the top of the mountain, right? So that's why, so you just know that the news about the vessel, the submarine vessel on the Indonesian Navy, all right? So what happened to the vessel? That's if there is some error due to the wall, okay, the wall of the vessel, okay. So if there's something, because the wall need to be designed so it can absorb a very high pressure at the bottom of the ocean. So we people, okay, we people, so if you swim, okay, inside the water, okay, we must, okay, we must equip ourselves with a special suit, okay. Say for example, as a diver, okay, because if you want to dive below, right, so we must have a special suit that we can actually feeling, okay, less pressure when we are going down inside the ocean, okay, compared to when we going, okay, when we going up to a mountain, okay. So when we going up to the mountain, we don't even need, okay, a thick, a special cloth, except because due to the weather, all right, because of the cold condition, okay. But if you are inside the water, so you need to have a special suit or special equipment, okay, because the pressure is high in the ocean. So that's why I refer back to the Indonesian Navy. So that's why it is very small possibility for them to survive inside the water, okay, when you are at very, very, at down below inside the ocean, because the pressure over there is very high. So if there is something wrong, if there is something wrong with the vessel, then of course the chance of you to live, okay, if you are not equipped with the special equipment, then they will die, all right, they will die over there. Okay, so that's the relationship of the pressure, okay, when with the height. Okay. All right, so we have a absolute pressure and gauge pressure. Okay. So when we saw that the pressure in a car tire is 3 bar, Okay, so 3 bar means that 3 times 10 to the power of 5 Pascal. All right, we mean that it is greater than the atmospheric pressure by this amount. Okay, so the total pressure in the tire is greater by P atm, the pressure of the atmosphere. So the excess pressure above atmospheric pressure is usually called as a gauge pressure. Okay, the total pressure is called as the absolute pressure. Okay, so when the pressure is less than atmospheric pressure, as in a partial vacuum, okay, the gauge pressure is negative. So inside the tire, okay, what you have here, so you have the pressure over here, and then over here you have pressure at the outside, P atm. Okay, so this PT, okay, is for the gauge pressure. Okay, so you have called the gauge pressure. Okay, the total pressure over here is called the absolute pressure. Okay, so that's the difference between gauge pressure and absolute pressure. So we have, this is the Borden type pressure gauge. It's connected to a high pressure gas line. Okay, so the gauge pressure shown is just over 5 bar. Okay, so this is the gauge pressure. So this is how you count the gauge pressure, as I mentioned to you about the car tire. Okay, so we have 5 bar as the gauge pressure. So this is normal when we go to the doctor. So the doctor will read our blood pressure. Okay, so our blood pressure inside our body, okay, give a reading of 130/80. Okay, give the maximum and minimum gauge pressure in the arteries. Okay, measured in millimeter, okay, Hg or Torr. All right, so that's the unit. So blood pressure varies with the vertical position within the body. Okay, so that's why, okay, to measure a correct blood pressure, so it is usually, okay, we need to sit up. Okay, we need to sit down. All right, we need to sit down on the chair, and then we put our hand on the table. Okay, because you can try that at the different position. If you have the tool, you can try to measure your blood pressure. Okay, so if you are not sitting up, or when you lie down, okay, on the back, okay, or you put your hands up, okay, try and measure your blood pressure. It will be different. Okay, because remember one principle, that pressure is always related to the height. Okay, so if you want to get accurate as much as possible, okay, the blood pressure will count for every person. So this is the point. Okay, the standard reference point is the upper arm level with the heart. Okay, where the point you measure, where the point that you measure must be horizontally, okay, at the same level as your heart. Okay, so your heart is over here, so you need to measure, okay, you need to measure the pressure somewhere over here. Okay, so then you will get, okay, a correct pressure, okay, for your blood pressure reading. So the normal pressure is 110/70. So if you are measuring, okay, at your heart level and also right, okay, in front or at your upper level of this arm, okay, then you will get a correct reference, okay, your correct blood pressure reading. Okay, so you get the concept. Okay, so you can also try if you want to check the blood pressure over here compared to here. You can try, so you see what's the reading. Okay. Also, you can try, maybe you can try to measure your blood pressure at your leg, right? To see, to prove that blood pressure is related to the height. Okay, you will see the difference in the reading. Okay, you can try that. All right. We have the Archimedes principle. Okay. So what is Archimedes principle? So let's say we have some arbitrary element of weight in equilibrium. Okay. So we have the weight of the weight somewhere there, and then we have the force B. Okay. The force due to the fluid element due to pressure must sum to a buoyant force. So B is a buoyant force equals in the magnitude to the element's weight. Okay. So that's the Archimedes principle. Okay, the fluid element replaced with a solid body of the same size and shape. Okay. So well, let's say you put a rock, okay, a rock inside the water. So you will have a buoyant force acting there. Okay. The force due to the pressure are the same. Okay. So the body must be acted on by the same buoyant force as the fluid element, regardless of the body's weight. Okay, for example, we had an object immersed in water seems to weigh less than when it weighed in air. Okay, so why is that happen? Okay, so you see that the buoyant force is acting on the weight. Okay, so the force due to pressure are the same. Okay, so the body must be acted upon by the same buoyant force as the fluid element. Okay, so that's why you have a lesser weight inside the water. Okay, you can put the scale, okay, inside the water, it will still work. Okay, you can put scale inside and then try to measure your weight, okay, inside the water and see what will happen to the weight. Okay, see what will happen to the weight. Okay, one more thing that I want to show. We have a real life example. For example, I have a watch. Okay, I have a watch. When you wear a watch, okay, so you look that inside your watch. So there's somewhere you mentioned that you can go. Okay, you can actually is 5 meter water resistance, 10 meter water resistance. So what's that mean? Okay, so that is actually related to with the pressure. Okay, what will happen if you exceed? Okay, if you wear a watch and you swim deeper, okay, you swim deeper inside the ocean and you're still wearing the watch. Okay, so one thing is because of the pressure. Okay, so because the pressure is very high down there, and then maybe your watch, okay, is not working anymore. Okay, because the water might be going inside the watch. Okay, so that's why when the watch is put with the water resistance, so it will put at a certain distance, okay, certain distance deep into the water. Okay, how is the height from the ground to the inside to the water? Okay, so that's one more example, okay, to the pressure. Okay, All right, so we have the Archimedes principle. It's also similar when we swim. Okay, when the object is less dense than the fluid, it floats. Okay, so that's why we can float our body. Okay, when we can make our body less dense. Okay, less dense than the fluid. Okay, so as ourselves, so the human body usually floats in water, and a helium-filled balloon floats in the air. Okay, because of the density of Earth is less than the water, then we can float. So these are the example of buoyancy. Okay, so this described by this Archimedes principle. Okay, so when an object is completely or partially immersed in a fluid, the fluid exerts an upward force, okay, on the object equals to the weight of the fluid displaced by the object. Okay, so let's watch a video over here.
Here I have two cylinders, the same size, but different materials. I have a steel cylinder and an aluminum cylinder, and as you can see, the weight
So they
is
have
much
different
different between the
weights.
two.
Okay.
Now I'm going to lower each cylinder into the beaker of water, and the question is, which scale will show a greater reduction in force? Will it be the one with the aluminum, the one with the steel, or will the reduction be the same for both?
Okay, the one we have 12, and the other one we have about 40 kilograms. Okay, so what it is asked over here, which one will show you the greater reduction? Okay, either the aluminium or the steel one. So the steel one weighs 40 kilograms, and the other one weighs about 15, somewhere 15 or 14. Yes, 14 kilogram. Okay. Okay, if 14 goes to 10, okay, so it's only about 4 kilogram reduction. But if 40 goes to 20, so the reduction is 20. So meaning that they still have bigger reduction. So what's your answer? Who chose A? So the aluminium cylinder. Nobody choose A. Okay, how about B? Steel cylinder. Okay, nobody choose B. And how about C? Reduction of the force will be same for both cylinder. Okay. So what is your answer? What answer that you choose?
C.
Okay, C. Okay, no, Sophia also choose C, isn't it? Sorry, so Sim also choose C.
Yes.
Okay. All right, Kaya also choose C. So, reduction in force will be the same. Okay, let's have a look.
As you can see, reduction in the weight is roughly equal between the two cylinders.
All right, good.
This is because buoyant force depends on the volume of an object and not the weight of the object.
Okay, so the answer is due to the volume, right? Due to the volume of the shape. Okay, so these two objects has similar volume. Okay. So that's why the reduction in the force is similar. Okay, so it doesn't involve the weight. Okay. All right, so that's why, even though, all right, you are, okay, you are a very fat person, right? You still can float on the water, right? Because your weight doesn't count when you are inside the water. Okay, so that's one example. Okay, so we have the concept of surface tension. Okay, so the surface of water acts like a membrane under tension, allowing this water strider to walk on the water. Okay, so this is the principle that you can apply. Maybe you can design a shoe, okay, an object, okay, that you can use to later, maybe if you want to walk on the water. Okay, so you can use this. All right, so we have a molecule, the water molecule. See, actually, we have a water molecule. Between all of those molecules, we are having the surface tension. Okay, so these molecules in liquids are attracted by the neighboring molecules. Okay, at the surface, the unbalanced attraction causes the surface to resist being stretched. Okay, the molecules in the interior are equally in all directions. So when this happens, okay, this tends to reduce the liquid's surface area. Okay, so the liquid surface area is reduced when we have the surface tension. Okay, so we have also the concept of fluid flow. Okay, so the path of an individual particle in a moving fluid is called a flow line. Okay? In a steady flow, the overall flow pattern does not change with time. So every element passing through a given point follows the same flow line. Okay. In a steady flow, no fluid can cross the sidewalls for a given flow tube. Okay. So you have the tube over here. So let's say moving in the tube. Okay. So we have a flow line. So these are the flow lines. So we have the flow lines. Okay, so the flow lines is there. So if it is a steady flow, the overall flow pattern does not change with time. So every element passing through a given point follows the same flow line. Okay. Let's say we have a tube. Okay, we connect it with a tap, and then we turn on the tap, and then the fluid, okay, we have the same fluid flow. Okay. So in a steady flow, when that happens, no fluid can cross the side walls for a given flow tube. Right? So that's why you see that when the fluid flow at very high pressure in a certain direction, it won't spread. It won't spread, okay, because it is flowing a fluid flow. Okay, if you turn on your tap, okay, if you turn on your tap in your bathroom and you pull it at a very maximum maximum flow, then you will see that, okay, the water, okay, will flow in only one direction. It won't spread over. So that's the relationship with the flow line right? So because the water cannot go outside that boundary, okay, the boundary of that side wall. Okay, so if we have we have also the concept of turbulent flow, okay, and also the laminar flow. Okay, in the laminar flow, adjacent layers of the fluid slide smoothly past each other, and the flow is steady. Okay, so you can see here we have a laminar flow over here. And then if we also have the turbulent flow, meaning that it is going some other way, okay, so there's a turbulent. At sufficiently high flow rates, okay, the flow can become turbulent, okay. In a turbulent flow, there is no steady state pattern, okay. The flow pattern changes continuously, right? So that's the difference between laminar flow and turbulent flow. Okay, so let's say, so you have a basin tap, okay, you have a basin tap, and then you have a tap, so you turn on, okay. So actually you try to keep the water, okay, you keep the water, and you see there is a difference when you tap it at the maximum pressure, at the maximum flow, and then to the small flow. So you see that there will be the fluid direction, okay, inside the water that you contain will be different, okay. So at the very high flow, you will see the turbulent flow. I mean, there is no exact flow line that you can see. But if you turn on the tap very at a small flow, then you will see the water will nicely have a flow line. Okay, so you can try that. You can see that. Okay, so that's the relationship of the fluid flow. Okay, so from there, okay, from the fluid flow, we can have a what we call the continuity equation. Okay, so what does the continuity equation tells you? So continuity equation is A1 B1 is equals to A2 B2. So that's related with the area, okay, with the area of the fluid line. Okay. So let's see. Okay, let's see at the figure over here. So we have the A1 over here, the area of the flow line. Okay, and then we have another area at flow 2. So we have a different area of the flow line. Okay. So this is related to the V, okay, volume of the water. Okay. So what's mentioned here, if the fluid is incompressible, the same fluid volume exits flow tube at the upper end as enters it at the lower end. So it is having the similar volume, okay. Sorry, it will be having similar volume, okay, exits at the end, okay, exits at the end of the other hole, all right, at the other hole of the end of the flow line. Okay, so let's say, okay, you turn on same water, okay, pouring the same okay, let's say you have a mug, all right, a mark over here, all right, a mark over here. Then you want to pour that into a bowl, all right, into a bowl. Whatever volume that you have over here, when you turn it over there, right, you will see that flow, all right, the flow when you pour that, okay, it will be big at the top, and then it will be smaller, okay, it will be smaller at the end of that, okay, as you can see from here, okay. This is the example. By the way, give me a couple of seconds. All right. So that's the concept of the continuity equation. Okay, and we have one more equation which is the volume flow rate. So the volume flow rate is dV over dt is AV. So that's the volume flow rate. And okay, so you will have also the Bernoulli's equation. Okay, so the Bernoulli's equation is given by this one, right? So where you have P1 pressure. So now you can relate that with pressure. P1 plus PGY1 plus half PV1 squared equals to P2 PGY2 plus half PV2 squared. Okay, so you can relate that with pressure. Okay, so pressure over here, okay, and the volume over here. Okay, so the Bernoulli's equation, okay, is actually expansion from the continuity equation. Okay, so we had the flow there, right, and then the pressure over here, I think over there, okay, will be PV2. Okay, P2 and PV2, and then you can see this is the P, okay, the P of everywhere, okay, the pressure of everywhere, and the P1 is at the initial, right? So P1 is at the initial pressure that you apply over here, and then P2 is at the other end. Okay, P2 is at the other end. So what is good over here that you can see that if you have a pipe, right? You have a bigger opening at one end, and then you have a smaller opening at the end. When you apply the pressure, okay, when you push something, so with a smaller pressure over here, and at the end of that, you can actually move that further away. Okay, you can move that further away because the pressure that you apply smaller over here will be bigger at the end. Okay, because the area over there, okay, so like this one, so I'm giving you an example. So let's say you have a cord there, and then you have another big cord over here, you apply the pressure there, so it will move further away, because the area is smaller over here, but smaller over here is big. So when you have small big area and then this one, so of course small pressure will give you big pressure over here. So because it will be similar, all right, because you use this is a Bernoulli's principle. Okay, so that's the relationship. All right. So let's have a 5-minute break. Okay, after this, we're going to go through some problem. Okay, we go through some problem. Okay, let's have a break for 5 minutes. Okay, right. You guys ready? You want some quiz today? So there is no penalty on the quiz, but the thing that, as I mentioned last time, so for those who get the highest mark, okay, we will get some bonus mark for their grades. So let's ready to play another quiz, all right? Okay, so I'm going to open this. Okay, you can. The address is joinmyquiz.com. So the code is 798233. Okay, so I saw Jai is there. I'm going to wait for 1 minute, so for you to join. Who is 209031? Just write your name. Okay, just write your name there. So it's easier for me to identify who you are. All right. So we have only 11%. How about the rest? Everyone else is not interested to join? Okay. I'm going to start the quiz from 10. All right, so everyone is ready. So I'm going to count 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, let's start the quiz. You can see your score there. complete the quiz before I end the quiz. Okay, only Munira and Farhana can see it. Okay, great. Okay, so that's the result. So he's got the first place, Elia got second one, alright, and Jai got the third place. Alright, and Alia and Akil got the fourth and fifth place. Okay, so I'm going to give a bonus mark for the top 5, right? For the top 5. So for those who haven't got it correct, okay, who haven't got the top 5 this time, will still get a chance. Okay. Alright. So that's, I don't think I have time to discuss you question, alright, on this topic. Okay, but never mind, we still have tomorrow to discuss during the tutorial. Okay, we will use some time during tutorial to discuss some of the question. Okay, so let's end today's class. All right, so before that, so let's turn on your camera. So for me to take the picture of everyone. Okay, I can see some happy faces from Jai today. Because she got one of the leaderboard for today's quiz. All right, so come on everyone. I'm going to count from 10. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Smile. Give me one more shot. Okay, thank you everyone. Okay, have a nice day. All right, so I'm gonna see you tomorrow. Okay, assalamualaikum and bye-bye.
Thank you, Doctor.
Okay, you're welcome.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor. Thank you, Doctor.
You're welcome.